This paragraph is watermarked. I put it there this morning. It is not a hidden character. There are none in the file. Not metadata either. 801 bytes of plain AXI and no secret label anywhere in it. The mark is not in the text. It is in which words got picked. And that should not be possible. An image hands you millions of pixels, nudge a few thousand, and nobody notices. A sentence hands you 20 words, and everyone is doing a job. The capital of France is Paris. You cannot mark that by changing Paris to London. And so, how do you hide a signal in ordinary English and add nothing to it and still find it later? Anthropic published the answer 6 days ago, and we are going to build it and run it. Everything you just heard, I read off a phone. I was running Teleflow, the sponsor of this video, a teleprompter that films you while you read. Manual shutter speed and exposure, so the picture is yours. Scripts sync over iCloud, and any computer on your Wi-Fi drives it from a browser, so your agent can write the script and push it to the phone. And the watch on your wrist is the scroll wheel. Teleflow, the link is in the description and the comment. Everything starts with one question. How does a model pick its next word? Not the whole sentence, one token at a time. Here is a real one, mid-paragraph. This endpoint acts as a, and now it has to choose. Inside every possible next token gets a raw score. Those are the logits. Softmax turns those scores into probabilities that add up to 1. Vital 6.2%, gateway 5.1, safeguard and check 4.8. Look how flat that is. 5 different words, and all of them are fine. And then the part that matters. It does not simply take the top one. It rolls a weighted die. Which is why you can ask the same model the same question twice and get 2 different paragraphs. That is not the bug. This is called sampling. And it means that almost every word there is slack. So every words would have been fine. Nobody can tell which one you took. Hold on to that because it is the whole video. The randomness was already sitting there. The watermark does not add anything to your text. It decides how the die lands. One more ingredient before we build it, a key. In our run, it has 9 numbers. Anthropic has 1. Google has 1. You're not getting it. And the key is the only secret in this whole method. Everything else is published. Remember it, it comes back at the end when we go looking. Here is the trick, and it starts with 4 words the model just wrote. Turn those into their token numbers, mix them with the secret key, and hash the lot. Comes out a single number, call it a seed. A seed is not mysterious. It is a way to get numbers that look random but repeat exactly. Same 4 words, same key, same seed every single time. The name for that is deterministic pseudorandomness. And it is why any of this works, because later we have to rebuild these numbers without being there when it happened. The seed does one job. It hands every candidate word a secret scorecard. In the paper, they call G values. Our run has 9 per word. 1 for each layer. The paper uses 30. Each one is just a 0 or 1. And here is the part everyone gets wrong. So I will go slowly. The probability comes from the model. It says how likely is the word there. The G value comes from the key. It says, does this word fit the secret pattern at this exact spot? They have nothing to do with each other. A 1 does not mean the word is better, and the same word in a different sentence scores differently because the 4 words in front of it changed the seed. This is that measured real model, real sentence, real numbers. The context is this endpoints act as a. Vital is the likeliest word at 6.2% and it scores 4 out of 9. Gateway 5 out of 9, safeguard 6. And check at 4.8% scores 7 out of 9. Check is not the likeliest word here. It is the word that fits the key best. And check is the one that came out. So you are probably thinking, fine, just always take the word with the most ones. That would work exactly once. Do that, and the model stops writing English and starts writing whatever the key wants. Everybody would notice by the second sentence, and the whole thing would be worthless. So it does not do that, it runs a tournament. First, it picks candidates the ordinary way. Using the models on probabilities, 8 of them repeats aloud. A word with a 10% chance turns up more often than a word with 2. A word with no real chance never gets into the room at all. So the model still decides who is competing. Then they fight in pairs. The higher G value wins the round. A tie is settled with a coin flip. 8 becomes 4, 4 becomes 2, 2 becomes 1. And every round reads a different layer of the scorecard. So winning early guarantees nothing. On our real sentence, check 1, this endpoint acts as a check-in point to confirm that all necessary components have been deployed correctly. Ordinary English, which is the entire point. Now the fair question, does rigging the die makes the writing worse? The Nature papers claim is stronger than you would expect. Averaged over the seed, the output distribution is unchanged. Google ran it live in Gemini across about 20 million responses. Thumbs up moved up by 1/100%. Thumbs down moved by 200th. Neither was significant. 15.5 milliseconds a token, about 0.5% slower. And it writes no extra tokens. So it costs the same to serve. If you want the rest of the stack pulled apart the same way, subscribe. Now the other half. And it is the same machine run backwards. You have a paragraph and nothing else. No hidden characters, no metadata, we checked at the start. But you have the key. So you walk the text and at every word, take the 4 words in front of it. Mix them with the key, same hash, same seed, same scorecard. You are rebuilding the coin flips without ever having been in the room. You do not need to know who the other candidates were. You never replay a single match. You ask one thing, did the words that actually made it into this text scores more often than the chance? Here is the whole thing. Import the config and the processor that goes with it, straight out of transformers. 9 keys and a 5 token window. That is the entire configuration. To write, you build that config and hand it to generate. That is the generation side finished. Detection is the same processor, pointed backwards. Compute the G value for the text you were handed, mask out the repeated context, and take the mean. That is it. Generation and detection in about 40 lines. So let us run it. 40 lines, load an open model, ask it the same question twice, once plain and once watermarked. This is Google's own implementation, the one shipped in Transformers, not Claude's. Claude has no public detector yet. Both paragraphs are perfectly readable and both answer the question. Now score them. The plain one comes back at just under a half. The watermarked one, 0.55. That gap is a whole watermark. And 0.55 sounds like nothing, so here is how to read it. If nobody touched the text, every G value is a coin flip, so the average lands on a half. Over 100 words, that average gets very tight, which makes a small push a very long way out. The plain paragraph landed just under a half. You would see that more than half the time by chance. The marked one is 3.5 standard deviation out, about 1 in 8,000. That is what detection is. Not a label, a number that says this did not happen by accident. Which means length is everything. Same marked paragraph cut shorter and shorter. At 15 tokens, about 1 in 10, that is not evidence of anything. At 176 tokens, about 1 in 100,000. The mark did not get stronger, there was just more of it to count. Which is why a tweet cannot be caught, an essay can. And then there is a place it cannot go at all. Remember the capital of France. Ask the watermarked model and it says Paris. 3 tokens, the detector will not even score it. There was no choice to make, so there was no room to hide. Ask it for code and the same thing happens quietly. 260 tokens, twice the length of the paragraph we got, and it comes back undetected. Anthropic says this outright. Where the output has to be exact, the watermark is not applied. What does a hit actually prove? This is Anthropic's own wording. A detected mark is a signal that the content was processed by Claude, but it is not fully conclusive. And no marks proves nothing at all. Paraphrase it, translate it, rewrite it, and it's gone. It cannot tell you a human wrote something. It cannot even tell you a different model wrote it. The only question it answers is how likely it is that this passage came through Claude, which is a much smaller claim than the one people are about to start making with it. Anthropic did not hide anything inside your words. They changed the coin they flip while choosing them. 40 lines and a key, and you can watch it happen on your own machine.